Alright, so this is a review video of physiology for this exam, starting with lecture 59, the basics. Here we have our nephron, and we know that we have blood flowing in through the afferent arteriole, into the glomerular capillaries, and then out through the efferent arteriole. And as we have our blood getting filtered, there's four different functions that the nephron is going to do. The first is our standard filtration, then we have reabsorption to the peritubular capillaries, and then we have secretion from the peritubular capillaries into the filtrate, aka the urine, and then finally excretion. So overall that gives us, excretion is filtration minus reabsorption plus secretion overall. All right, and then we have the concept of excretory rate, and so excretory rate is of a substance is the concentration of that substance in the urine times the urine flow. And then that's equal to what we call the filtered load, the filtration rate times the concentration of that substance in the plasma, so how much is getting filtered, minus the reabsorption rate, so what's being taken out of the filtrate, plus the secretory rate, what's being put back into the filtrate. All right, so that is excretory rate, how much substance is being removed per unit time. Then we have the concept of clearance, which is a little bit different. This is the amount of plasma per unit time that is cleared of the substance. So excretory rate is how much substance per unit time is being removed. Clearance is how much plasma is getting cleared of the substance. All right, and so clearance is equal to excretory rate divided by the plasma concentration of a substance. Okay, that brings us to our four basic substances that we need to know. The first is inulin. You see inulin is in addition to like fiber bars as fiber, but inulin is filtered only at the nephron. It is not reabsorbed, it's not secreted, it's only filtered. All right, so inulin is only filtered, and so that means that the clearance that it has is a good estimation of the glomerular filtration rate. All right, then we have creatinine, which is filtered, and then a tiny amount is secreted. And we use creatinine as an estimate of the glomerular filtration rate because unlike inulin, which doesn't naturally exist in the body, our body is constantly producing creatinine as a result of just having muscles, like a byproduct, a waste product overall. All right, so that brings us to our third equation, creatinine, clearance of creatinine, since it's filtered plus a very small amount is secreted, it's really this filtration rate that we care about, is a good estimation of the glomerular filtration rate. Okay, so the creatinine, the clearance of creatinine is a good estimation of GFR. Then we have PAH, and PAH is filtered and secreted, but not reabsorbed. And importantly, PAH, because it's filtered and secreted, right, both of these are driving fluid into the urine, substances into the urine. At low concentrations in the plasma, PAH is entirely excreted. So you can use the clearance of PAH as a good estimation of renal blood flow. So the clearance of PAH is a good estimation of renal plasma flow. Okay, our fourth substance is glucose. It is filtered and then reabsorbed. Importantly, it is at low concentrations entirely reabsorbed. Then we have the next equation is effective renal blood flow. So the effective renal blood flow is the estimated renal plasma flow, which we estimate with the clearance of PAH, divided by 1 minus the hemocrit, because renal blood flow, renal plasma flow, plasma is just the blood minus the red blood cells, the hemocrit. Okay, then we have the concept of filtration fraction, and so this is how much of the renal plasma flow gets filtered at any given time. It's generally around 20%, so filtration factor is equal to the glomerular filtration rate over the renal plasma flow. All right, you can estimate this as clearance of creatinine over the clearance of PAH. All right, so that's the first lecture. The second lecture was on regulation of glomerular filtration hemodynamics. So we're really familiar with these concepts, so I don't want to spend too much time on it, but basically it goes back to Starling forces and then the flow of liquid in relationship to pressure and resistance. So we know that Starling forces are about the pressure pushing fluid out minus the pressure pulling fluid back into a capillary. And so basically the premise is that you have the oncotic pressure due to the proteins is going to increase the further along the glomeruli and into the efferent capillaries, because you're removing filtration from the protein stays, but other things get removed from the plasma, or from the blood, excuse me. All right, so that version of that gives us the glomerular filtration rate, which is just Kf, a filtration coefficient, times the Starling force pressure. So this equation we're very familiar with. It's just, instead of a Q here, we're putting GFR. And then we have this equation, the Van 't Hoff equation, which is osmotic pressure is equal to N times CRT over M. N is the number of particles which a substance dissociates. C is the concentration, right? So N would be like NaCl, breaks down into two substances, so N equals 2 for NaCl. M is the molecular weight, R is the universal gas constant. I can only assume this will be given to us, and then T is the temperature in Kelvin. All right, that brings us to renal blood flow. So renal blood flow, just like any generic blood or flow of liquid, we denote with Q, or we can denote with Q, and so Q is equal to change in pressure over resistance. So flow is caused by change in pressure, limited by resistance. And for our nephron, we said that we had the afferent arteriole and efferent arteriole. And so the afferent arteriole, A at the beginning, is constricted by the sympathetic nervous system with neuro and epinephrine. The sympathetic nervous system also works on the efferent, but it works on it less. And so the afferent arteriole is going to be a primary control mechanism. And then the efferent arteriole, under sort of standard conditions, efferent arteriole is constricted by angiotensin II, which is ultimately comes as a result of the renin angiotensin system. And we know that renin is going to be released by cells in the juxtated glomerular apparatus in response to increased sodium levels or increased stretch, all right, of that region, distal tubule passing by the glomerulus. All right, what happens when efferent or afferent arteriole gets constricted? So it's really the point here they're saying is, you can manipulate the GFR and the renal plasma flow by constricting either the afferent or efferent arteriole, right? And so if you constrict the afferent arteriole, which is the case with the SAS, then if you constrict here, then you can get a chokage of blood in this region, right? And so less blood is going to get to here. So the pressure in the glomerulus falls. If the pressure in the glomerulus falls, then there's less pressure pushing us to get filtration. So filtration will go down if the afferent arteriole is constricted. All right, and if this is constricted, then we just have less throughput, right? So the renal plasma flow is going to decrease as well. If the efferent arteriole is instead constricted, then you get a buildup of fluid here, and so you have this pressure is going to increase. And if this pressure increases, then the GFR is going to increase, and with any sort of restriction, you have a decrease in renal plasma flow. All right. So we said that this change here, SAS, this change here would be more due to angiotensin too. All right. So in terms of autoregulation, we have the basics, myogenic regulation, which is this is arterioles are surrounded by smooth muscle. So smooth muscle will respond to a high blood pressure, aka a stretch, by contracting. So it's the myogenic automatic response. And then you have tubuloglomerular feedback. And so we have on this vascular pole, if we go to our histology material, we have the juxtaglomerular apparatus here with the macula densa. And so in that region, you're going to have the juxtaglomerular cells are going to sense an increase in sodium and an increase in flow. And as a result, the cells in that region will release renin, which will result in an increase in angiotensin 2, right? Tensin those angio blood vessel tensin. So it's going to constrict the efferent arteriole. And as a result, if the efferent arteriole is constricted, then you have a decrease in glomerular filtration rate, decrease in renal blood flow. All right, but why would this occur? High blood flow, this would be indicative of a high blood pressure, right? All right, so moving on, that brings us to lecture 61. And so lecture 61 and lecture 62 are talking about maximum transport mechanisms. And so really this is starting to talk about, we talked about our example filtrates. And so we had inulin, which we said was a fiber. We have creatinine, which is a waste product from muscles. We have PAH, which I believe is not normally present in the body. Then we have glucose, which we know is. And so if you have secretion in the case of PAH, or you have reabsorption in the case of glucose, well, it's going to need a transporter to do that. And so just like any enzyme, these transporters can get saturated. And so then you have the concept of TM, which is transport maximum. And for glucose, which is reabsorbed, the transport maximum corresponds to reabsorption, right? And so the only equation we had from this lecture was this idea that glucose is going to get entirely reabsorbed until it reaches a threshold value of concentration in the plasma. And so once it reaches that threshold value of concentration in the plasma, then the transporters for reabsorption of glucose are going to be saturated, and any excess glucose that has made it into the filtrate is going to be excreted. So you have a threshold plasma concentration, and the idea is that the reabsorption rate here will meet a maximum reabsorption rate, which we call TM. And so TM, the maximum reabsorption rate, where you have a saturation of your enzymes, is going to be equal to the filtration rate, glomerular filtration rate times the threshold plasma concentration of glucose. All right, so the maximum reabsorption rate is equal to the glomerular filtration rate times your concentration at the threshold, which is again right here, right as you start to excrete glucose because your enzymes are saturated. All right, what are those enzymes? Great question. All right, so to start this discussion off, we're very familiar with the concept of the nephron having different parts. So we have the proximal tubule, the descending loop of Henle, then we have the ascending loop of Henle, we have the distal tubule, then we have the collecting duct, right? And so the different regions of the nephron reabsorb and secrete different things, depending on the purpose. And so this proximal tubule here is where the majority of reabsorption occurs, right? And so, I can already sort of show you here for sodium, 66% of sodium gets reabsorbed, same with water and potassium and chlorine in this region. For metabolites that are at usual concentration, 100% of them are going to get reabsorbed. This is glucose, amino acids, proteins, ketone bodies, and then bicarbonate, around 80% is going to get reabsorbed in this region. And so the challenge is we have a lot of things getting reabsorbed here. So what are all of the different transport mechanisms? I think it's pretty gnarly. All right, so the basics is sodium is super important for reabsorption. Why? Well, we've already talked about water follows sodium, but potassium and chlorine also follow sodium. But importantly for all of the nephron, sodium is going to be used as a concentration gradient that can drive the co-transport of different things. All right, so in particular, we have the very first one is sodium on the apical surface of the proximal tubule will get co-transported with glucose in our sodium-glucose link transporter 2. And basically, we would call this a secondary active transport because on the basal and the lateral side, we have this, we're very familiar with this from other physiology, but we have the sodium-potassium ATPase, which is pumping sodium out of the cell and bringing potassium in. And so that results in a low sodium concentration inside of the cell, which results in sodium being brought in. All right, but this ATPase uses ATP, so all of the different transporters in the proximal tubule that use sodium, we would to co-transport, we would define as secondary transporters, secondary active transporters. All right, so then in addition to glucose being reabsorbed by the sodium-glucose linked transporter 2, you have glucose on the basal membrane will go from high concentration to low concentration back into the blood through the use of the GLUT2 channel. We have amino acids are also being co-transported. We have three different types: basic, acidic, or other. And then lactate would be co-transported with sodium. And then importantly, we have phosphate being co-transported with sodium, and that can be either 2 sodium with dihydrogen phosphate, or it can be 3 sodium with monoprotonated phosphate. All right, then the phosphate will leave the basement membrane via an anion phosphate co-transporter or anti-transporter here. Okay, so why do we care about phosphate? Well, phosphate will act as a buffering system for hydrogen ions later on. All right, so then we have the hydrogen ion transporters in this region. And so here we actually have an anti-transporter with sodium going in, hydrogen ion coming out. We also have a hydrogen ion ATPase in this region to pump hydrogen ions out. This is important because we have hydrogen ions are going to allow the reabsorption of an important molecule, which is bicarbonate. And so bicarbonate in the filtrate, the urine filtrate, is going to combine with hydrogen ion from our with our help of our friend carbonic anhydrase, and it will importantly turn into carbon dioxide through this enzyme. Carbon dioxide can diffuse through the cell membrane to be retaken up into the cell, and then once it gets into the cell, it can use carbonic anhydrase again to reform our bicarbonate, and then our bicarbonate will leave the cell via a sodium co-transporter. All right, and so in this region, you get reabsorption of bicarbonate through this pathway overall. All right, so then we have excretion of organic anions and organic cations in this region. And so organic anions, we were just told in lecture that they use a tertiary active transport to accomplish this. And I don't have any more details on that, unfortunately, but good to know that organic anions and cations are reabsorbed or are secreted or going into the urine in this region. Then we have organic cations, and we're actually told there's 2 different transporters that we should be semi-familiar with. At least you can hear the word. We have our organic cations, will include things like PAH, penicillin, urate, and morphine. And so you have the MATE transporter, MATE, which stands for multi-drug and toxin excretion transporter. And then you have an ATPase, MRD1, and MRD1 stands for multi-drug resistance protein. Okay, but organic cations and organic anions are going to be secreted into the urine in this region. All right, then we also have urea is being reabsorbed in this region, and about 90% of it gets reabsorbed. All right, final thing to talk about is the effect of angiotensin and neuro and epinephrine from the SAS. So angiotensin 2 is going to stimulate these sodium potassium ATPases, and neuro and epinephrine will also stimulate the sodium potassium ATPases. And so angiotensin 2 will cause by stimulating the reabsorption of sodium and drive all of our reabsorption mechanisms as a result. Same with the sympathetic nervous system with neuro and epinephrine. All right, angiotensin 2 will also stimulate the sodium hydrogen ion exchanger, and those are the 2 things we need to know in this region. All right, lecture 63 got into the medullary gradient, and so basically the idea is that we have the descending loop of Henle, and the descending loop with a D is P permeable to water, all right, and relatively impermeable to solute. All right, so water can leave this region, but solute is pretty much not going to move at all in the descending loop of Henle. Then you have the ascending loop of Henle, and A and I in impermeable to water. So ascending is impermeable to water, but these solutes will get reabsorbed. All right, and so we have basically within this region, we have countercurrent in the loop. So we have down and up, and then we also have a countercurrent from the blood vessels. That's really the more important one, and that will help allow the creation of a super concentrated interstitial fluid in this region. Okay, so let's take a look at the actual cell so we can look at the transporters overall. So we have the thick ascending loop. In the thick ascending loop, we have on the apical surface adjacent to the urine, we said thick ascending loop A and I, this is impermeable to water. Okay, so impermeable to water, in this region we have a sodium hydrogen ion exchanger, just like we had in the proximal tubule, that is stimulated by angiotensin 2. And then the important one is we have sodium potassium chlorine co-transporter called NKCC2, and so this guy will bring sodium ions, chlorine ions, and potassium ions into the cell, and this is a potential target for pharmacology as a diuretic, because if you increase the concentration of these guys in the lumen, well, water is going to be drawn in through osmotic pressure, right? And so if more of these are in the lumen, then more water is going to be in the lumen. More water in the lumen, more water in the urine, you're going to pee more, so you have a diuretic. All right, then in this region we also have a channel for potassium to leave, and so when potassium leaves through this channel in this region, you actually create a positive membrane potential, and that positive membrane potential on these thick ascending loops are actually going to drive calcium ions and magnesium ions paracellularly back into the interstitial fluid, into the blood. And then on the basement membrane of these thick ascending loop cells, you have something called the calcium sensing receptor, CSR, which will take calcium in, and then it will actually cause an inhibition of the NKCC2 co-transporter. And, why would that be an important thing? Well, you bring in less potassium. Less potassium means less potassium transported out through the leak channel here, less potassium transported out, less of a positive membrane potential, less calcium brought paracellularly. All right, so thick ascending loop has this tertiary co-transporter, and it has the calcium receptor. And then on the basement membrane, just like the other cells, you have the sodium potassium ATPase, you have a chlorine potassium co-transporter, and then you have a bicarbonate channel. All right, so we've left the thick ascending loop. Now we're on our way to the distal tubule, and so we have proximal and distal tubule. Proximal is going to be impermeable to water, or distal tubule will be permeable to water. And so this region is going to reabsorb calcium, sodium, chlorine, water, and bicarbonate. And importantly, the distal tubule in the reabsorption of sodium and chlorine has a sodium-chlorine cotransporter, and this is a target for thiazide diuretics, and they block this cotransporter of sodium and chlorine. And so the idea is, by blocking this, you are going to result in an easier uptake of calcium due to a decrease in sodium in the cell, which increases calcium reabsorption. Why would this be the case? Well, in the basement membrane, you have a sodium-calcium anti-transporter, and so if there's less sodium inside of the cell due to an antidiuretic, or a diuretic, working on inhibiting this guy, you'll actually have more calcium taken up. All right, in this region, you also have a calcium ion channel on the surface, which is going to be stimulated by parathyroid hormone. And then, importantly, these distal tubule cells will express calbindin, which is synthesized by the cell, or expressed by the cell, and calbindin binds calcium to support the uptake of calcium, and its synthesis is stimulated by vitamin D. All right, then we have our standard sodium-potassium ATPase stimulated by angiotensin 2, neuro, and epi. And then we do have a calcium ATPase in this region, and then chlorine can leave via chlorine leak. All right, but calcium reabsorption, and then we have a target for sodium chlorine overall. All right, and or the target for diuretic, which targets the sodium chlorine cotransporter. Then we have the collecting duct, and so the collecting duct we know is right here, and it's going to do a lot of water reabsorption via aquaporins. And importantly, it's the collecting duct is the target for aldosterone, an antidiuretic hormone, also called vasopressin. And in particular, we have two types of cells in this region. We have principal cells, which are more numerous, and this is going to be where these two guys put in their work. You can see that here. The principal cells are more numerous, and then we have intercalated cells, and we actually have two types of those, alpha and beta. But you can see principal is more numerous, and then the two stain different shades. Right? So the more numerous one is principal cells. All right, so the principal cells in particular. So to start off, we have these special channels called the epithelial sodium channel, ENAC, and this is just going to bring sodium ions into the cell. And then the reabsorption of sodium, we said that chlorine follows sodium, but in this region, it's not a one-to-one sodium-chlorine following, and so the net result is you actually get a negative membrane potential form because you're having all the positives go into the cell, right? So the outside becomes more negative. As a result, this increases potassium reabsorption in this region, okay, or potassium secretion into this region, into the urine. All right, this is a target for pharmacology. These ENAC channels are a target for potassium-sparing diuretics, because if you block this guy, then you're not going to create this negative membrane potential, which is not going to help pull out the potassium ions, and so you won't secrete as much potassium, and so you can have the effect of a diuretic increasing the sodium content in the urine to therefore increase the water content in the urine, while maintaining without losing potassium at the same time. All right, you can also have action on aldosterone receptors or aldosterone production. And why does aldosterone matter? Well, these principal cells have receptors for aldosterone, which is a mineralocorticoid, and they are going to increase the number of these ENAC channels and increase the amount of time that they stay open. They're also going to increase the synthesis of our standard sodium-potassium ATPase overall, which we know angiotensin 2 and neuroepinephrine stimulate as well, or stimulate the action of. All right, so if aldosterone is causing an increase in ENAC channels, it's going to increase the uptake of sodium, which will result in an increase in the secretion of potassium. And so potassium-sparing diuretics could also target aldosterone to increase sodium in the urine, increase water, increase urine, but spare potassium. All right, we also have urea reabsorption in this region. We have water coming in via aquaporins too, potassium's leaving via leak channels, which we talked about. And then importantly, our aquaporin, we have antidiuretic hormone, right, which says save the water. ADH, also called vasopressin, will act on receptors in the principal cells that will stimulate a GS-coupled receptor, or that is a GS-coupled receptor pathway. That's going to increase the number of aquaporins expressed by the cells via an increase in CAMP, and then that will have a secondary effect of increasing urea reabsorption. All right, so these are the principal cells, the target of aldosterone and antidiuretic hormone. All right, then we have our intercalated cells, and we have alpha and beta cells, and you can see them here. The alpha cells both of them are important for acid-base regulation, and in particular, the alpha cells have these potassium hydrogen ion exchangers, and so potassium will be brought into the cell, hydrogen ion will be secreted into the urine. Then you also have hydrogen ion ATPases, and our aldosterone stimulates our hydrogen ion ATPases, which pump hydrogen ion into the urine. We also have potassium leak channels to go into the blood, and then we have a bicarbonate and chlorine ion exchanger anti-transporter. Beta intercalated cells have this transporter on the apical membrane. Apical membrane being this membrane right here. All right, so a lot of information, and the intercalated cells start to bring us to our next topic, which is the topic of lectures 68 and 69, which is acid-base balance. All right, and so basically, we want to know what the kidney does to help maintain physiological pH. So our standard pH is 7.4, and we have a standard bicarbonate value of 24, and can see the units here. Then we have a standard partial pressure of carbon dioxide as 40 millimeters of mercury. So in terms of looking at these questions, we have a 3-question method. So what is the osis? If you have a pH less than 7.4, you have acidosis. If you have greater than 7.4, it's alkalosis. The next question you ask is, what is the cause? Is it respiratory acidosis, metabolic acidosis, respiratory alkalosis, metabolic alkalosis? And then has there been compensation by the body? And the idea is that, depending on the cause and the compensation, you can sort of diagnose what is going on. All right, so the 4 primary disturbances to body pH, we said we have respiratory acidosis. So basically, if you aren't breathing enough, then you have a buildup in carbon dioxide, right? Because it's a waste product from respiration in our body to produce ATP. Buildup of carbon dioxide is going to drive this reaction to the left. It's going to result in an increase in hydrogen ion and an increase in bicarbonate. Okay. To compensate, our kidneys are going to eliminate hydrogen ion because you're in acidosis, or you want to reduce acidosis, and it's going to conserve bicarbonate. And then the idea is that if you take a look at the levels of bicarbonate in the blood and partial arterial carbon dioxide gas, for every 1 millimeter of mercury increase in the partial pressure of carbon dioxide, you should have a 0.1 milliequivalent per liter rise in bicarbonate. And if this is a chronic case of respiratory acidosis, you'll have a larger increase at 0.3 for every 1 millimeter of increase in partial pressure of carbon dioxide. All right, so then we have metabolic acidosis. Basically, your blood is acidic, but not because of breathing. You just have, for whatever reason, you've had an increase in hydrogen ions or a loss in bicarbonate, and that's resulting in a decreased pH. And so, as we have here, an increase in hydrogen ions or a loss of bicarbonate. And so how does the body compensate for this? Well, an increase in breathing to drive this equation to the left an increase in breathing is going to reduce carbon dioxide and therefore reduce this guy, hydrogen ion. All right, and you also have a decrease in bicarbonate, but overall you should be able to get an increase in pH as a result of a loss in hydrogen ion. All right, and then you can check if the body is well compensated by using something called Winter's equation, which you can see here. You calculated predicted partial pressure of carbon dioxide by multiplying 1.5 times the value for bicarbonate and then adding it to 8, and then the measured. If you're well compensated by your respiratory system, then the partial pressure of carbon dioxide should be within plus or minus 2 of this. If it's not, then you're uncompensated. All right, respiratory alkalosis is breathing too much, and as a result, you don't have enough carbon dioxide. This shifts the reaction to the left, meaning a decrease in bicarbonate, a decrease in hydrogen ion. The result is you have an increase in pH, which is alkalosis. The kidneys are going to respond. Same thing. You can check the bicarbonate versus partial pressure of carbon dioxide to see if you're acute or chronic, meaning compensated or uncompensated. You should have a 0.2 decrease in bicarbonate for every 1 millimeter mercury increase in partial pressure of carbon dioxide, decrease, and then 0.5 decrease if it's compensated. All right, and then finally we have metabolic alkalosis. And so alkalosis is increased pH, so loss of hydrogen ion or an addition of bicarbonate. And then because it's metabolic, you're going to breathe in order to compensate for this. So to fix this, you're going to breathe less to have a buildup of this guy. A buildup of this guy is going to increase your hydrogen ion concentration to decrease pH and get you out of an elevated pH, get you out of alkalosis. All right, here we have a compensation chart. So basically trying to figure out what's going on. So again, we start off with what's the osis, or you look at your pH. If you have a low pH, you're acidosis. If you have a high pH, you're in alkalosis. After that, you look at the cause. So in particular, you can look at bicarbonate ion. Bicarbonate ion, if it's low, then you have metabolic acidosis. If it's high, you have respiratory acidosis. In the case of alkalosis, if your bicarbonate is low, you have respiratory alkalosis. If it's high, you have metabolic alkalosis. All right, and then this logic is basically this whole part written out. The best way to do it is just look at this equation, for each scenario and figure out what's going on. All right, then we have the Davenport diagram. And so the Davenport diagram is basically we're looking at, we have the normal value of pH, we have the normal value of bicarbonate. And so if you know these two values, then you can figure out if you're in acidosis or alkalosis. And then by graphing it, you can figure out if you're compensated or uncompensated. And so this red line right here is the typical deviation of pH and bicarbonate under respiratory disturbance. If you're in this region, it's a respiratory acidosis. If you're in this region here, it's a respiratory alkalosis. And then the purple line is a curve. And if you're in this region, it's the typical deviations under metabolic disturbances. If you're in this region, it's metabolic alkalosis. If you're in this region, it's metabolic acidosis. All right, so acidosis to the left, and then you go from there. Okay, here we had some example questions. In the interest of time, I'll let you do those yourself, but you can take a look at them. These dots right here are some examples. So here you're going to have the orange arrows are the body's attempted compensations. So if you're right here, you can see that we're within the respiratory acidosis region. And so this is the typical response to, or this is the typical, the red line is the typical deviation. So if you're right here, you can see that we have moved, just draw arrow in that direction. You can see that we have moved towards a normal pH. So this would be a compensated respiratory acidosis. If we were right here, if our value gave us a number on the red line, we would be in uncompensated respiratory acidosis. Similarly, if we were here, then we would be in uncompensated metabolic alkalosis. If we were here, you can see we're more towards normal pH right here. So this would be compensated metabolic alkalosis. If we were right here, we're in the metabolic acidosis region. You can see that we are closer to the normal pH. So this would be compensated metabolic acidosis. If we're on this part right here, this would be uncompensated metabolic acidosis because we're on the line. Same thing here. If we're here, this is respiratory alkalosis. And if we're on the line, we're uncompensated, we're acute. And then if we're here, then we're closer to the normal pH. That means that we are in compensated respiratory alkalosis. All right, so this last part is just a little bit of other buffering systems. We have acetic acid. We'll break down to hydrogen ion acetate, which is conjugated base. So acetic acid can be a buffering system. Blood, in particular hemoglobin with its imidazole, can take up hydrogen ions and so act as a buffering system. So carbonic acid, which we know from this guy right here is carbonic acid. Carbonic acid plus hemoglobin with its imidazole will give a hydrogen ion to imidazole. And then we're familiar with our bicarbonate carbon dioxide buffer system with our friend carbonic anhydrase mediating it. All right, and then one last thing, we had metabolic acidosis. So if we're in this region, down here, again, along the lines is the typical deviations. If you're acute, and if you're off the line, you're compensated in some way, right? All right, so metabolic acidosis, there's actually a tool called the plasma anion gap to help you determine what's the underlying cause. And so the idea is that cations and anions in the blood have there's an equal charge, right? So the net charge in your blood should be approximately 0 because the number of positives from cations and the number of anions should be equal. However, if you look at specifically just a subset of the cations and anions, you can actually come up with something called the anion gap, which can be useful. So if you just look at sodium as your cation and you just look at chlorine and bicarbonate as your anions, sodium's normal value is 140, bicarbonate's is 24, and chlorine's is 104. And so if you add up these two guys, they do not equal the sodium ion. And so you naturally have this anion gap if you use these two. And so if you measure the serum sodium and bicarbonate and chlorine, then you can calculate this guy, and basically that value should typically come out to be plus or minus 12, right? So if you take this guy plus this guy, it is 12 less than this guy. So 12 plus or minus 2 is our typical value. And so if you have an elevated anion gap, you've measured this and you've measured this, and you see that these, for whatever reason, these two are low, such that the gap is greater than 14, then the typical underlying cause is from mud piles. And mud pile stands for M is methanol, U is uremia from kidney failure, D is diabetic ketoacidosis, P is paraldehyde, I is iron, and I is sonacide, L is lactic acidosis, E is ethylene glycol, ethyl ketoacidosis, S is salicylate starvation, ketoacidosis, and sepsis. And then if you don't have an ion gap, and you are in metabolic acidosis, your pH is low, if you have no anion gap, then hard up is used. H is hyperchloremia, A is acetaldehyde, R is renal tubular acidosis, D is diarrhea, U is urethral diversion, and then P is pancreatic fistula. All right, so that's it for this physio review for this exam. Good job, you did it.